We now turn our attention to the second part of the analysis of case study ex2. Part 2 of this case study focuses on the implementation of the BuggyFactorial and SynchronizedParallelFactorial classes that use shared mutable state incorrectly and inefficiently. The code we're about to walk through can be found in the ex2 project in the FP folder of my modern Java GitHub repository. We're back in the IntelliJ project for case study ex2. This time, we'll take a look at the mutable state file, which is in the algorithms package. This file contains classes that use Java objects with shared mutable state to either incorrectly or inefficiently compute factorials for BigInteger objects. We'll start our analysis by looking at the BuggyFactorial class, which shows how race conditions can occur when mutable state is shared between threads in the Java common fork join pool using a Java parallel stream and the for each terminal operation. Inside of the BuggyFactorial class is a nested class called total. And this class stores a running total of the factorial and also provides a Buggy method to multiply this running total by a value of n. Class total contains a single field called mtotal of type BigInteger. This field contains the running total of the factorial, which is shared mutable state that's not protected by any synchronizer. So of course, this is going to lead to chaos and insanity here shortly. We initialize mtotal with the 1 constant from the BigInteger class. There's also a mult method, which multiplies the running total by the value of n, which is the parameter. However, since the code shown here is not synchronized, race conditions will be incurred when run on a multi-core processor. You can see what we're trying to do is we're trying to multiply mtotal by n and then update the value of mtotal. However, there's opportunities for race conditions galore here, as we'll see when we actually run the program. Let's now go take a look at the factorial method for BuggyFactorial. This attempts to return the factorial for the parameter n. The result, however, will be inaccurate since there are race conditions due to accessing and updating shared mutable state, namely the total class object and the mtotal field within that object. As you can see here, the first thing that the factorial method does is it makes a new local variable of type total called t. However, this object will be incorrectly shared by multiple threads in the Java common fork join pool, as we'll see momentarily. Here's the actual stream implementation. As with the sequential stream factorial class, we create a stream of longs from 1 to n using the range closed factor method on the long stream class. This time, however, we use the parallel operation in streams to arrange to run the stream operations concurrently in the common fork join pool. The next thing that happens is we use the map to obj intermediate operation to convert each long value to a big integer using the value of factor method. And then finally, we use the for each terminal operation to multiply each value in the stream by the running total. However, we're passing in the mult method reference on the t object. However, t has side effects that are not synchronized properly, and therefore race conditions will occur when this runs in the context of a multi-core processor. Finally, we return t.mtotal as the result from the factorial method. What we're trying to do is we're trying to give back the final total. However, this will incur memory visibility problems on multi-core processors since the calling thread will likely be different from the pool of worker threads, and therefore the values won't be propagated properly throughout the memory hierarchy. So as you can see, there's a number of problems with the BuggyFactorial implementation that will lead it to yield incorrect results due to race conditions and memory visibility problems. We'll now turn our attention to the SynchronizedParallelFactorial implementation, which attempts to rectify some of the problems with the BuggyFactorial implementation we just looked at. This implementation shows how Java synchronized methods can inefficiently avoid race conditions when state is shared between threads in the Java common fork join pool. As with the BuggyFactorial implementation, the SynchronizedParallelFactorial implementation also contains a nested class called total, which stores a running total of the factorial and is properly, albeit inefficiently, synchronized to avoid race conditions and memory visibility problems. As before, this class total also has an mtotal field of BigInteger type, which is initialized to 1. As we'll see, however, this field will not incur race conditions, even though it's shared mutable state, since it's protected by the Java intrinsic lock that's associated with an instance of the total class. The total class also defines a method mult, which multiplies the running total by n. Mult is implemented as a synchronized method, which means that only one thread at a time can be running mult on a given object of type total. Although this synchronized method avoids race conditions, it incurs excessive contention on the intrinsic lock associated with the instance of class total. Class total also defines the getSynchronized method, which returns the final value of the factorial computation. This synchronized method ensures visibility of the result in multi-core processor memory. Let's now take a look at the factorial implementation in the SynchronizedParallelFactorial class. This method inefficiently returns the factorial for the parameter n using a Java parallel stream and the for each terminal operation. As with the BuggyFactorial implementation, this factorial implementation starts by creating a mutable shared object called t of type total. This object, however, is correctly, though inefficiently, shared by threads in the common fork join pool since it's properly synchronized using Java synchronized methods. The actual stream implementation here is identical to what we saw before in the BuggyFactorial implementation. We first create a stream of longs from 1 to n using the range closed factor method on the longstream class. We then use the parallel intermediate operation to run all the operations concurrently in the common fork join pool. We next use the map to obj intermediate operation to convert each long value to a big integer. And finally, as before, we use the for each terminal operation to multiply each value in the stream by the running total by passing in the t mult method reference. In this case, the code will be correct because it's synchronized properly. However, it's inefficiently synchronized due to the contention on the intrinsic lock of type t. Finally, we return the total, which will be visible to the calling thread since it's also protected by t's intrinsic lock. So as we showed in our analysis of the SynchronizedParallelFactorial class, it's possible to implement shared mutable state correctly. However, it's also likely to have inefficient results by having to use synchronized methods in places that incur excessive overhead due to contention on intrinsic locks or other types of synchronizers. So that's the end of part 2 of our case study ex2 analysis, where we focused on the incorrect and inefficient use of shared mutable state to implement factorial algorithms.